Let me introduce this system. Step 1. The camera captures a frame at a pretty small resolution, 160 by 120 pixels. Keeping it small is what makes the processing fast enough to run in real time. For every pixel in that frame, the code checks whether blue is clearly stronger than red and green. If it is, that pixel gets counted as part of the ball. Step 2. It averages the positions of all those blue pixels to find the ball's center point, then compares that to the center of the frame to get an error value. Basically, how far off to the side the ball is. Step 3. A PD controller decides how fast the servo should spin. The proportional part is simple. The bigger the offset, the faster it spins toward the ball. But on its own, that causes a problem. As the camera catches up to the ball, it doesn't slow down in time, so it overshoots, swings back, overshoots again, and the whole thing starts oscillating. Adding a derivative term fixes that. It looks at how quickly the error is shrinking and applies a braking effect proportional to that, so the camera actually decelerates as it approaches the ball instead of blowing past it. Step 4. That calculated speed gets sent to the servo. Since this is a continuous rotation servo, it doesn't take an angle. It takes a speed and direction. So the code sends a value centered on a stop pulse, with the offset from that value controlling how fast and in which direction it spins. If the ball isn't found at all, the servo is stopped completely as a safety measure. Those 4 steps just repeat over and over, so the camera is constantly trying to recenter on the ball. Every time it turns, the next frame shows a slightly different view, and that continuous loop is what produces the tracking behavior. Right now, the tuning values are proportional gain 22, derivative gain 12, a 10-pixel dead zone around the center, and a stop pulse of 90. I'm still adjusting these numbers to find the point where the motion stays smooth and stable.